Welcome back to the course of Applied Elasticity. In today's lecture, we are going to continue with our discussion on the topic of thermoelasticity, which we had started in our last lecture. So, thermoelasticity deals with the solution of the problems, the deformation of the elastic continuum when it is subjected to combined mechanical and thermal loading. So, both mechanical and thermal loads are acting on the elastic body, and if we are interested to solve for the stress distribution and deformation of such elastic continuum subjected to combined thermomechanical loading, that is called the thermoelasticity problem. The total strain for thermoelasticity problem is summation of the mechanical strain and the thermal strain components. Now, this thermoelasticity is important, or this study is important for various engineering applications such as the thermal power plant component analysis, the turbine blades and different IC engine parts which are subjected to thermal shocks, the aircraft structures being subjected to cyclic aerodynamic heating, and the welding and coating. For these different applications, the components are subjected to the thermal loading as well as mechanical loading. So, the solution approach of thermoelasticity is required to be used for solving such problem. In the last lecture, we had obtained the thermoelastic constitutive relation, that is the relation between the stress and strain components for any thermoelastic problems, and also discussed about the basic formulation of planar thermoelasticity under two types of assumption, plane stress problem and plane strain problem. Now, in this lecture we are going to solve a specific problem, which is a thin circular disc subjected to axisymmetric temperature variation. So, the thermal loading is applied to a thin circular disc, and we are interested to find out the stress distribution generated and the resulting displacement of this thin circular disc subjected to axisymmetric temperature variation. So, let us consider this circular disc which is having some small thickness in z direction. So, xy is the in plane direction. We will be using the polar coordinate, that is r theta coordinate, for solving this problem. And as you know, the thickness of the disc is assumed to be small. We can model this as a plane stress problem. Also, as it is subjected to axisymmetric temperature variation, and the geometry of the body is also axisymmetric, disc is axisymmetric, and hence this overall problem can also be treated as an axisymmetric problem. So, this problem is an axisymmetric plane stress thermoelasticity problem. It is plane stress problem, it is also axisymmetric problem which is subjected to the axisymmetric temperature variation. So, for the plane stress problem, we have all three out of plane stress components, sigma zz, tau rz and tau theta z to be 0. So, these three out of plane stress components are 0 from the plane stress assumption. Now, from the axisymmetric assumption, another stress component tau r theta is 0, and all the quantities or all the field variables are independent of theta. So, del theta, partial derivative of any quantity with respect to theta is 0. So, that is the assumption coming from the axisymmetric problem. So, tau r theta 0, del theta of any quantity 0, this is axisymmetric assumption. Sigma zz, tau rz, tau theta z 0, this is plane stress assumption. And as this present problem for the thin circular disc subjected to axisymmetric temperature variation is an axisymmetric plane stress problem, all these assumptions are valid here. Now, we are assuming the temperature field to be function of radial coordinate r, independent of field variable theta, and then only it is axisymmetric temperature variation. If in case you are having t as a function of both r and theta, then we cannot call this to be an axisymmetric problem, because T would be dependent on theta. As it is axisymmetric temperature variation, T can only be function of R. So, along the radius from center to the outer radius, we are having a variation in the temperature of the disk, of the thin disk, and we are interested to find out the stress and deformation of this particular disk. So, strain components for this axisymmetric plane stress problem can be written like this. As it is a plane stress problem, the out of plane strain components are not there. We are only going to consider the in plane strain components. We are interested with the in plane strain components, two normal strains epsilon RR and epsilon theta theta, which are written as summation of mechanical strain and thermal strain as epsilon RR is 1 by E times sigma RR minus nu sigma theta theta plus alpha t, epsilon theta theta is 1 by E times sigma theta theta minus nu sigma RR plus alpha t, the thermal part, and epsilon r theta is 0. For the axisymmetric problems, epsilon r theta must be 0, as we have tau r theta, the corresponding shear in plane shear stress, to be 0. Now, moving to the stress components, in terms of the strain components, we can write the stress component sigma RR as E by 1 minus nu square times epsilon RR plus nu epsilon theta theta minus 1 plus nu alpha t. The another normal stress sigma theta theta can be written as E divided by 1 minus nu square epsilon theta theta plus nu epsilon RR minus 1 plus nu times alpha t, and tau r theta, the shear stress, is 0. Now, moving forward, these stress components are now substituted in the equilibrium equation. So, as it is a polar coordinate problem which is axisymmetric in nature, the equilibrium equation in theta direction is automatically satisfied. Also, as this is a body with small thickness in z direction, thus with plane stress assumption, the equilibrium equation for the z direction would also be satisfied automatically. Now, in absence of any body force, the only equilibrium equation which we need to satisfy under this assumption of axisymmetric plane stress problem is the r direction equation of equilibrium, which is d sigma RR dr plus sigma RR minus sigma theta theta by r equals to 0. And note that here the stress component sigma RR and sigma theta theta are function of the single variable r. They are independent of the second variable theta. Now, replacing sigma RR and sigma theta theta, these stress components in terms of the strain component epsilon RR and epsilon theta theta in this equilibrium equation, in absence of any body force, it would be like this. So, I am replacing both the stresses, both the normal stress components in terms of normal strain components in the equation of equilibrium, and then if I simplify this, the first term is having a derivative with respect to r, the radial variable. So, if I take the derivative of all these three terms with respect to r, then this equation can be rewritten like r times ddr of epsilon RR plus nu epsilon theta theta, then plus 1 minus nu times within bracket epsilon RR minus epsilon theta theta. This is equals to 1 plus nu times alpha r dt dr. Note that this t is function of radial coordinate r. This is not a constant. So, once you are taking time derivative of the derivative of this term with respect to r, radial variable, we would be treating 1 plus nu and alpha as constant, but t is dependent on r, it is function of r, that is why we are having a non-zero dt dr term coming from this, and which we are writing on the right hand side. This is a temperature field with a variation in radial coordinate along the radial coordinate. Now, moving forward, these strain components epsilon RR and epsilon theta theta in this equation are now written in terms of displacement component. Now, if you recall about the axisymmetric formulation discussed earlier, for axisymmetric problems we have u theta, the displacement along the angular or tangential direction. U theta must be 0 to maintain the axis symmetry of the deformation, and hence the only non-zero displacement component is u r, that is the radial displacement, with respect to which the strain components can be written as epsilon r r is d u r dr and epsilon theta theta is u r by r. So, these are the two strain components, two normal strains written in terms of the radial displacement component u r for the axisymmetric problem. So, replacing epsilon r r, epsilon theta theta here as du r dr and u r by r respectively. These equation can be simplified in this form as d2 u r dr 2 plus 1 by r du r dr minus u r by r square is equals to 1 plus nu times alpha dt dr, and hence writing this left hand side, this particular function of u r, rewriting it in this form, which is ddr of 1 by r ddr of r u r, that is the left hand side, and this similar form of governing equation on the radial displacement we had earlier used for the other axisymmetric mechanical problems such as thick cylinder deformation. So, here also the left hand side is written in a similar fashion, whereas right hand side is non-zero here. For purely mechanical problem, dt dr term is 0, right hand side was 0. Now, as it is a thermomechanical problem, we are having right hand side to be 1 plus nu times alpha dt dr, and solving this equation u r, the radial displacement of the disc, can be obtained as C1 r plus C2 by r. These are the two terms coming from the homogeneous solution. These are the complementary function. If right hand side is 0, then these two terms C1 r plus C2 by r terms would be coming, which were there for a purely mechanical plane stress axisymmetric problem. Now, along with that, as the right hand side is non-zero because of presence of this temperature variation, we would be having an extra term, that is the last term, which is the particular integral term in u r, which is 1 plus nu times alpha by r integral a to r t r dr. Now, what is this small a? Small a defines the inner boundary of the disc. So, integral starts from inner boundary of the disc and going till any radial coordinate value r. With this, we are getting the u r, the radial displacement at any value of r. If it is a solid disc, for that case a value is 0, inner limit of r is equals to 0, and then for annular disc we will be having r to be starting from some inner radius r I, and that would be equals to a. So, this equation gives us the displacement field for this thin circular disc subjected to axisymmetric temperature variation. Now, substituting these result of u r in the strain component, we can obtain epsilon r r, epsilon theta theta in terms of the C1 C2. Then substituting those back in the stress components, we can obtain the stress component sigma r r and sigma theta theta of this problem in terms of these two constants C1 and C2. So, epsilon r r is obtained as E by 1 minus nu square C1 times 1 plus nu minus C2 by r square times 1 minus nu. So, this part was earlier there for mechanical problems. Now, additional term in the radial normal stress is minus alpha E by r square, then integral a to r t r dr. So, this term is the contribution from the temperature field variation. Similarly, sigma theta theta would also be having two term. One was the existing term for mechanical problem, which is E by 1 minus nu square times C1 1 plus nu plus C2 by r square 1 minus nu, and apart from the first term, these second two terms, second and third, these two extra terms are coming in a sigma theta theta due to temperature variation, which are alpha E by r square integral T r by d r from small a to r minus alpha E t, where small a defines the inner boundary of the disk. Now, note that these first two terms C1, C2 being constant, E and nu being material constant, these first two terms for sigma r r can be written as some A1 minus B1 by r square, and for sigma theta theta this is A1 plus B1 by r square, which are the typical form of the two in plane normal stresses for any axisymmetric 2D problem. Now, along with that, we are adding these additional terms. For the getting these additional terms, because of the temperature variation, for sigma r r only one extra term is there, T dependent term, whereas for sigma theta theta two such T dependent terms are there. So, this is in general formulation for any axisymmetric problem, plane stress problem subjected to temperature variation. Now, let us consider two cases. One case is a solid disk subjected to temperature variation, another case would be annular disk subjected to temperature variation. So, first case is we are considering a solid disk of outer radius small b, which is subjected to the radial temperature field T as a function of r. So, for this particular case, the r radial variable r is varying between 0 to b. Hence, the lower limit of r being 0, value of small a would be 0. Now, for such cases, if the origin of the domain is included within the domain, origin of the coordinate system is within the domain. So, r equals to 0 is a point within the domain. To ensure the finite value of stresses or to avoid the singularity at the origin r equals to 0 point, we must force this constant C2 to be 0. With that, the infinite stress values at the origin can be avoided. So, one of the constant C2 is forced to 0 in these stress equations sigma r r and sigma theta theta. Thus, we would be having only one constant left, that is equals to C1, which is required to be evaluated. So, C2 is 0 for the solid disk problem. Now, for finding C1, we need to use the surface traction boundary conditions. Now, here the problem which we are considering is only subjected to temperature variation. No other mechanical loads, no other pressures are acting. So, this outer boundary at r equals to b is stress free. So, this is free of any kind of normal or shear stresses. So, using that boundary condition, that is sigma r r, the normal stress, normal radial stress on outer boundary r equals to b is 0. We can evaluate this value of C1. So, substituting sigma r r at r equals to b to be 0, we can evaluate this constant C1 as 1 minus nu times alpha by b square integral 0 to b T r dr. Note that these integral limit small a is nothing but 0 for the solid disk. So, we got this expression of C1 using the mechanical stress traction free boundary condition. Substituting these C1 back in the expression of sigma r r, sigma theta theta and u r, we can get the stress and displacement components for this particular problem of the solid disk subjected to temperature variation. So, stress components would be obtained like this: sigma r r is alpha e common term times 1 by b square integral 0 to b T r dr minus 1 by r square integral 0 to r T r dr, and sigma theta theta would be alpha e is common term, then 1 by b square 0 to small b T r dr plus 1 by r square integral 0 to r T r dr minus T, where T is the radial temperature variable variation field. So, these are the two stress components along the two normal direction r and theta for the present problem, and substituting C1, obtained expression of C1 in the UR radial displacement with C2 to be 0, we can get UR, the radial displacement for this circular disk, solid circular disk, to be 1 minus nu by b square times alpha r integral Tr dr from 0 to b plus 1 plus nu alpha by r integral Tr dr 0 to r. So, this is the radial field, radial displacement field for this particular solid disk. Now, considering the center at this point O, which refers to r tending to 0 or r equals to 0 point. For that, if you look at the second term of the displacement, we are having r in the denominator. With r tending to 0, this particular term will go to infinity unless we force this total r dependent part is equals to 0 at r limit r tending to 0. Hence, to ensure the 0 displacement at the center. So, center point, this problem being axisymmetric, center point must have 0 radial displacement. To ensure the UR, the first term due to presence of this r in the numerator, if r is 0, first term of UR will directly go to 0, no problems are there with that. Whereas, the second term can be 0 only if we ensure that limit r tending to 0, 1 by r integral Tr dr from 0 to r is equals to 0. So, the given temperature field Tr must satisfy this condition to avoid the infinite or large value of radial displacement at the center. Limit r tending to 0, 1 by r integral Tr dr from limit 0 to r must be equals to 0 for the given temperature distribution. However, this problem is not be there, will not be there in the stress field. Even though in the stress field you can see these second terms are having this distribution 1 by r square times integral Tr dr at r tending to 0. This 1 by r square will also try to go to a higher value. However, for these variations, this limit r tending to 0, 1 by r square integral Tr dr from 0 to r is a constant value, which is normally obtained equals to T naught by 2, with T naught being the temperature at the center. So, for all possible temperature variations, radial variation with T naught being the temperature at the center, and then it is varying either linearly, parabolically, exponentially, whatever, that r function can be anything. For all such cases, we can obtain, we can verify that this limit r tending to 0, 1 by r square integral 0 to r Tr dr would come out to be T naught by 2, which is a constant. So, stress distribution is finite at the center, and to ensure the 0 radial stress, radial deformation at the center, we must enforce this condition, limit r tending to 0, 1 by r integral Tr dr from 0 to r is 0. So, this is the discussion about the solid disk. Now, moving to the second case of axisymmetric annular disk of inner radius A and outer radius B subjected to temperature variation Tr, axisymmetric temperature variation. So, this annular disk is considered, inner radius is A, outer radius is B. So, two boundaries are existing, inner boundary is defined with small r equals to A, outer boundary is defined with small r equals to B, and body is subjected to temperature variation Tr. So, here the boundary conditions at inner and outer boundary both are the radial stress sigma Rr is 0 at inner boundary r equals to A, sigma Rr is also 0 at outer boundary r equals to B. So, using these two boundary conditions in the expression of sigma Rr, both the constants C1 and C2 can be obtained, and for this case both of them would be non-zero constants. For the solid disk, C2 was 0, C1 was only non-zero, but for annular disk both C1 and C2 would be non-zero constants, which are obtained like this. C1 is 1 minus nu alpha by b square minus a square integral a to b Tr dr, and C2 is 1 plus nu alpha a square by b square minus a square integral a to b Tr dr. So, these two constants are obtained by using the surface traction boundary condition, that is normal stress 0 at the inner and outer boundary of the annular disc. Now, substituting this C1 C2 back in the stress components equation, the stresses radial stress sigma RR and hoop stress sigma theta theta can be obtained like this, where you can clearly see this effect of temperature field T is present. Now, in this problem we are for both the solid and annular disc, we are only considering the effect of temperature variation. Along with that, some other mechanical forces or pressures can also be there. Let us say along with this, some external pressure P naught is acting on this disc. So, for that particular case, you need to modify the outer boundary condition, sigma RR at R equals to B would be minus P naught. For that case, sigma RR at R equals to A would be 0. If inner pressure is also there, then sigma RR at R equals to A should be written as minus Pi. So, like that, based on the different mechanical loads acting on the system on this axisymmetric body, you need to change the boundary condition along with the thermal loading, and for such cases the sigma RR and sigma theta theta would be having some extra terms which would be dependent on Pi and Po, that is the inner and the outer pressure. So, those would actually be a thermomechanical problem where both mechanical and thermal loads are acting. So, earlier we had solved the mechanical problems, the axisymmetric problem subjected to the mechanical pressure, inner or outer pressure for thick cylinders or compound cylinders. Now, we had solved the problem when it is subjected to temperature variation, and these can be easily combined by adding the required boundary condition sigma RR at R equals to A and B in terms of inner pressure Pi and outer pressure Po. So, in this lecture we had discussed about the problem of thin disc with axisymmetric temperature variation, and temperature variation effect is considered for both solid disc as well as annular disc. So, with this we are coming to the end of this course of applied elasticity. So, here I am showing or presenting the list of the books which you may refer for further details for this course on applied elasticity. So, at the end I want to thank all the contributing team members, both my teaching assistants Mr. Purushottam Nanda and Mr. Aniket Singh, who had helped me for development of this course contents. So, I also acknowledge my thanks to the technical support team of NPTEL office of IIT Kharagpur, from which Mr. Devopriyo Chakraborty, Mr. Devesh Prasad, Mr. Saurabh Bhattacharya and Mr. Dibyendu Sarkar has helped for development of this course, managing the course portal, video recording and editing the content. So, I express my sincere thanks to all these team members for helping and recording these video lectures. So, thank you all for attending this course. If you have any doubt or query regarding any of the topics, you may contact me over email. Thank you once again.